Okay, we're going to aim maybe a dart gun at an object, and as soon as we fire the dart gun, the object will start falling. And we want to prove that it's possible, if conditions are correct, that this thing here, let's say our projectile is going to go like this, and it'll hit about right here, and that our object would have fallen to be at this position here, and that they would still get hit. So again, if conditions are correct, we shoot the arrow at the same time an object starts to fall. So we want to show that that's actually possible. Well, let's get started. Again, we know we've got velocity in the x direction here, and we have a beginning velocity in the y, v sub y is 0. And what we want to do is prove that it's possible that the height of the arrow and the distance it goes in the x direction matches the height of our object within the same time. And of course, also the x direction would be the same. So let's go ahead and start. Well, we know that the displacement of the dart, I'll just use the letter d for that, is going to equal v naught times the cosine of theta multiplied by t. And then again, if we solve for time, time is then going to be our x value divided by v naught cosine theta. Okay, so let's go ahead and deal with the y component then of our dart. Y is going to equal v naught sine theta t minus 1/2 gt squared. Okay, now what about the monkey? Well, we're going to call this, maybe I better put a sub d here so we can keep track. That's the dart, or the object. Let's call it an object. Typically it's a monkey, but in here we'll just do an object. So the y then of the object is going to equal our height that the object is minus 0t, because remember the object's not traveling in the y direction initially, minus 1/2 gt squared. So here's the stationary object initially, it's just going to fall downwards. But we have a beginning displacement equal to h if we have our origin located here again on the ground. So our arrow, or our dart, has a beginning velocity or beginning displacement of 0 in the x and 0 in the y, but our beginning object displacement is h. So what we want to do is set both of these equations equal to each other, okay, and see what happens. So I've got then h minus 1/2 gt squared is equal to v naught sine theta t minus 1/2 gt squared. Now we set those two y equations equal to each other because we know that the two have to have the same height if they are going to intersect here, or the dart's going to hit our falling object. And we find out, of course, that our 1/2 gt squareds would cancel out. So we're left with height equals v naught sine theta t. Well, remember that t is also x divided by v naught cosine theta. So let's go ahead and plug that in. So h is equal to v naught multiplied by the sine of theta, and I multiply that by our time, which is actually x divided by v naught cosine theta. Well, we can cancel some things out there. Our v naughts can cross off. Sine over cosine is equal to the tangent. Therefore, h is equal to x tangent of theta. And then taking x to the other side, we find out that tangent theta is equal to x over h, which indeed is true. Here's our arrow right here. Okay, if I take a look right here and draw a triangle here, I'm just going to kind of draw a triangle here. Okay, we indeed see that the tangent of the angle theta, and again imagine our triangle here, is h over our x displacement that it goes. Since that is geometrically true, we have proven that with the correct conditions, an object that is falling when it gets shot at the same time by a dart or whatever will get hit on the way down.